In the previous episode, we saw how we broke through the walls of the CPU and how graphics cards transformed into the engines of intelligence. But as neural networks grew, standard gaming silicon was no longer enough. The world needed dedicated monsters capable of processing intelligence at a pure and brutal speed. This is Axiom Tech, and I am Epoch. Today we enter the battlefield of nanometers, terabytes, and megawatts. Behold the engine of the modern world. This is not a graphics card. It will not render a single frame of Fortnite or GTA 5. It has no HDMI port. The NVIDIA H100, the Tensor Core GPU. It is arguably the most complex technological artifact mass-produced by humanity. It is a data center GPU, designed to do one single thing: process transformer math faster than anything else on Earth. To understand how it achieves its awe-inspiring performance, let's examine it, layer by layer, from a digital design engineering perspective. When you look at an H100, you are not looking at a single chip. You are looking at a 2.5D advanced packaging miracle. At the center is the compute die, manufactured with TSMC's custom 4N 5nm process. It contains 80 billion transistors. But the real magic is not just the transistor count. It is the specialization of those transistors. For decades, scientific computing relied on high precision, FP64 double precision, or FP32 single precision. This meant using 64 or 32 bits of data to represent a single number, providing incredible accuracy to many decimal places. But AI researchers discovered something critical. Neural networks were surprisingly resilient to noise. They did not need perfect accuracy during training. Good enough is good enough. If you could shrink your numbers from 32 bits to 16 bits, or even 8 bits, you effectively double or quadruple your throughput and memory capacity instantly. You can move twice as many numbers through the same wires in the same amount of time. NVIDIA leaned into this hard. The H100 was specifically designed to excel at low-precision math. The secret weapon of the modern NVIDIA GPU is the Tensor Core. A standard CUDA core is like a scalar calculator. It takes a number, adds another number, and gives you the result, one operation per clock cycle. The Tensor Core is different. It is a specialized matrix math engine implemented directly in silicon. In a single clock cycle, the fourth-generation Tensor Core inside the H100 can perform a full matrix multiply-accumulate operation on 4×4 matrices using low-precision types like FP8. Instead of one math operation per cycle, it is doing hundreds. It is specifically hardwired to accelerate the exact math that defines deep learning. It is like having a CPU with a run Photoshop filter instruction built directly into the hardware, rather than running thousands of small software instructions to do it. But as we discussed with the CPU, having a fast processor is useless if you cannot feed it data, and feeding an H100 is a terrifying engineering challenge. Traditional DDR memory sticks are not fast enough. They are physically too far away, and their interfaces are too slow. The solution is HBM, the high bandwidth memory. Instead of placing memory chips flat on a motherboard, HBM stacks them vertically, like skyscrapers. They are connected vertically through the silicon itself using thousands of microscopic pathways called TSVs, or through-silicon vias. This entire stack is placed on a piece of silicon called an interposer, just millimeters away from the GPU compute die. The result is awe-inspiring bandwidth. An H100 with HBM3 memory has a memory bandwidth of over 3 terabytes per second. To put that into perspective, you could download the entire high-definition Netflix catalog through that memory pipe in less than a second. It is the only way to feed 80 billion transistors and keep them from stalling. From an RF and digital design perspective, this is nightmare territory. Running thousands of data lines in parallel, millimeters apart, at these speeds creates massive signal integrity issues. Crosstalk, noise, timing skew. The engineering required to keep those signals clean is just as impressive as the computation itself. But a single GPU, even an H100, is not enough to train GPT-5 or Kimi-K 2.5. You need thousands of them working together. If you connect GPUs using standard PCIe, it will be simply too slow. The GPUs spend too much time talking to each other and waiting to synchronize, instead of actually computing. NVIDIA's solution is NVLink. NVLink is a proprietary, ultra-high-speed connection that allows GPUs to talk directly to each other's memory, bypassing the host CPU entirely. It links multiple GPUs together, so they appear to the software as one single, giant GPU with massive memory. In an H100 superpod, the bandwidth between the GPUs is faster than the memory bandwidth inside most normal computers. The H100 is a synthesis of the absolute cutting edge of every single discipline of electrical engineering and materials science, all focused on a single purpose: matrix multiplication at scale. It is a magnificent machine, but its dominance has created a monoculture. And in technology, monocultures rarely last forever. The competitors are waking up. Right now, NVIDIA controls probably 90% or more of the AI training hardware market. Their dominance is built not just on great hardware, but on the CUDA Moat, 15 years of software tools that make developing on NVIDIA chips the easiest path. But the industry is desperate for alternatives. The chips are too expensive, too hard to find, and the power consumption is becoming unsustainable. The world needs competition. The biggest threat comes from the companies with enough money to build their own silicon. The hyperscalers, like Google, Amazon, and Microsoft. Google realizing early on that they did not want to be dependent on NVIDIA, and Google built the TPU, the Tensor Processing Unit. If the CPU is a Swiss Army knife and the GPU is a bucket of hammers, the TPU is a laser-guided missile designed for one specific target. The TPU is not a general-purpose chip. It is an application-specific integrated circuit, or ASIC. It is hardwired specifically for TensorFlow workloads. Its core architecture is a systolic array. Instead of fetching data, doing the math, and saving it back to memory repeatedly, a systolic array pumps data through a grid of processors in rhythmic waves. Inputs flow in, collide at intersections to perform multiplication, and the results emerge from the other side. It is incredibly efficient for matrix math, minimizing memory access, which saves a massive amount of power. Google uses these to train their massive models like Palm and Gemini. Others are trying more radical approaches. If the problem is moving data between chips, why not just make one giant chip? This is Cerebras. They don't cut the silicon wafer into small chips. They use the entire wafer to build a single massive processor. There are almost 1 million cores on a single piece of silicon. From a digital design perspective, this is madness. The yield issues, dealing with inevitable defects on the wafer, and the challenges of delivering thousands of amps of power and cooling a plate-sized chip are monumental engineering hurdles. But if it works, it completely eliminates the interconnect bottleneck. We have talked about nanometers, terabytes, and petaflops, but right now, the most important number in AI might be the megawatt. Current generation AI training runs consume electricity on the scale of small countries. A single H100 GPU can draw up to 700 watts of power. Pack thousands of them into a data center, and you need infrastructure capable of delivering tens of megawatts of power, and equally importantly, infrastructure capable of removing tens of megawatts of heat. We are reaching the limits of air cooling. Now we are pumping dielectric fluid directly onto the silicon to keep it from melting. We are converting electricity into intelligence, but the exchange rate is brutal, and the primary byproduct is waste heat. For 50 years, we relied on Moore's law, the observation that we could shrink transistors and make chips faster and more efficient every 2 years, which gave us free performance upgrades. But Moore's law is dying. We are hitting the fundamental limits of atomic physics. You cannot make a transistor gate much smaller than a few silicon atoms, and yet the demand for AI compute is growing faster than anything we have ever seen in technological history. This is the central conflict of our time. The unstoppable force of AI demand meets the immovable object of physics and energy infrastructure. Something has to give. Either we find radically new architectures that are orders of magnitude more efficient, inspired by the 20 watts used by the human brain, or we face an energy crisis triggered by our desire for synthetic thought. We built the engines. They are magnificent, terrifying furnaces of silicon. Now the question is, can we keep feeding them without burning everything down? This is Axiom Tech, and I am Epoch. We do not believe in magic. We believe in the brutal reality of engineering. In the next episode, we will look beyond the hardware and the software. We will look at the impact. What happens when these engines run at full speed? Stay tuned.